Hey everyone, welcome to Jai with Judah, the series where we talk about the Jai programming language. In this one, we're talking about the modify directive, which allows you to control polymorphism in your program and do a couple wacky things as well. And in Jai, we can make a polymorphic procedure similar to how we make a normal one. So if I'd have a little add function with a left side and a right side, we can make this polymorphic by replacing this int with $t. And what that does is that tells Jai the type of L must be inferred at the call site, and then that will be what T means in the rest of the context of the body. And so we can also replace these other two ints with T, and then just return L plus R, right? Because we're just doing a simple add function. So now, if I go and print, 1 plus 2, I get 3. Right? And I can add another print in here just so we can see what T actually is, and it's an S64. If I do this again with, say, 3.14 and 1.1, I get, float 32 and 4.24. Right? So now we've been able to use the same body of our procedure with different types. And you might be thinking, that's cool, but let's break it really quick. Right, if I do false and false, we now get a big error, right? And that says operator plus does not work on this type, bool and bool. So Jai still caught us. It still gave us an error at compile time for passing in, invalid types here. But these types are invalid because the operator plus doesn't work on them, right? The procedure itself still type checked. It still allowed L and R to be passed in. It's just once it got to checking the body, it realized that plus isn't allowed for Booleans. So let's actually add in, some extra layers of security, quote unquote, to our procedure. Well, we can do that with hash modify. You can think of hash modify as a procedure, as a simple procedure that takes in whatever type parameters we've defined as its arguments, and it returns a Boolean that says whether the modify passed, and then an error, right? An error string. And so in this case, it'll be T is a type, and that returns a bool and additionally a string. And so this is what modify actually looks like. And now that you've seen this, you might be thinking, okay, well, how do we actually introspect on T and check that it matches the constraints that we've set? Well, if we go into our modify and we print T and we execute this, we'll get a compiler error, but it's for a different reason, right? Not all control paths return a value. And so if we remember from this procedure example, right, you can see why we get that error, because we didn't return a Boolean. So if I return false here and I still print out T, we get error modify returned false. But we do get this print statement actually executing where we get S64. Right, and so T in this case is an S64. So if I run type of on T, we'll see that we get just the word type. And what that means is that we can actually cast this capital T type into something that we can introspect on. And that is called type info. So if we do, info is cast to type info of T, and we run this again, but this time printing the dereferenced value of T, we get something that kind of looks like a struct, right? It has these curly braces, has the word integer, and then an 8. And so let's jump to what type info is. And you can see that type info actually is a struct, right? And it has two members, one being a type info tag and one being a runtime size. And if we look at this type info tag, you can see integer, right? And so you can think of type info as the thing that describes your types, right? It's how the compiler understands your types, right? Or understands what types are, and it exposes that information to us so we can introspect and do fun things with it. And it just so happens that we can convert a capital T type into a type info pointer. Jai allows this to happen. And it just so happens that this is just a simple downcast, right? Type itself is a pointer to type info. And so let's add some constraints to our add function. Let's say we only want integers and floats to be passed in. Right, so now we can do info.type is integer, or info.type is float. And let's just give it a little error message. And we can actually also use formatted strings here by calling tprint. And because this is all run at compile time, it'll actually, run tprint at compile time and give us that formatted string. So we can do add only allows integers and floats given, some other thing, t. So now if we run this, everything will pass and it'll be back to how it was earlier. The difference now is that if we do that false, false again, and we execute the program or compile the program, so we modify return false, add only allows integers and floats given bool. Right, so now we've introspected on the types that were passed in, and we've had, some extra checks at compile time and given another error message. And we can extend on this further by changing how our body or how the body of our function reacts to, whatever type is or whatever t is in this case. So if I do if t and I do a compile time switch, right, so we could handle each t or each type that gets passed in separately if we wanted to, right? But you might be thinking, oh, that's a lot of like separate code paths to do all this. So let's add some more constraints. So what we can do is, because modifies can actually be chained together and they run in order. So this first modify will get executed. And so that'll just check if t is a numeric type. And then the second modify, let's have that check the runtime size to rule out, 8 and 16-bit integers, as well as, all unsigned. So let's do this. So if info.type is integer, we are going to cast that to a type info integer. If we jump to type info integer, you can see that it is a type info, and it just has a member called signed. And then for our floating point case, or for our float case, we just want info runtime size greater than or equal to 4. So now if we run this, see add only, we get that same error, but the original case will still work because we have both these modifies. They run in order, and the first one will pass because it's an integer or a float, right? It's a numeric type. And the second one will pass because the default types given to integer and floating point literals is S64 and float 32 respectively. And so we've cut down all of our cases to basically just be S32 and S64, float 32 and float 64. So if we really wanted to, we could, have an assembly block in here that uses instructions specifically for signed 32-bit integers. We could have one for signed 64-bit integers as well as floats. And so we have a ton of control over what our function actually does, or what a procedure actually does, based on the types that are passed in. Let's clean up our example a little bit, right? Let's make a procedure called type is numeric. And that's going to take in a t, and that's going to return a Boolean. And it's just going to do this, right? That's all it's going to do. Right, but now this will still work. So you can kind of clean up your modifies to not just be a block, right? We can have another one called number is 64 or 32 bits. Return number is 64, 32 bits. And there we go. Now, not only does modify work for procedures, but it also works for structs as well. So let's impose the same restrictions on our foo struct as we did this add function. Well, luckily for us, we can literally do this. And this will now work. So I can now make a foo, and I'll do it in here just so it's a little more clear. I can make a foo with, say, type U8 is what I'm polymorphing over. And now we get this modify return false because this second one failed, right? So the first one passed, the type was numeric, but the second one failed, right? It was not a 64 or 32-bit number or numeric type, right? And so that is the nice thing, is that we can use modify for structures and for procedures. Now, one quick thing about how the $T works, or how this, polymorphic type declaration works, is that when you see the $, that is when the type is first defined or declared in that parameter list. And so that is where the type will be inferred from and assigned when checking the rest of the parameters. If I set, L to be $T, that means that we're looking at this first argument, or Jai, when it's type checking, is looking at this first argument, and then after it infers that, it will assign T to be whatever type that it inferred. Now, if I change the position and put it to R, right, this is allowed, but the second argument will be inferred and will be used to type check the first argument and the return type, right? So you can define it or declare, $T in any place, in any position in the function, but that is where it will be used to infer the type. And we can see that if I do, a little print in here, T, you can see that we get S64 and float 32 as we'd expect. But now if I do this, cast U8 of 1, and then cast of float 64 of 1.1, we get U8 and float 64. But let's move on to something a little weirder that we can do with hash modify. So we can delete this $T from the second argument and instead put it on the return type, which doesn't make sense on its own, right? What we have told Jai, or the compiler, is that, hey, infer the return type of T some way, like somehow infer this, and then type check L and R to be that return type, right? So you might be thinking I could just do this, but we get an error, right? Compile time variable T is needed, but was not specified. And that is because in this procedure header, T is never defined anywhere, right? We've declared it as a thing that we want to define, but we have no way to define it. But we can do this. And this will, if I do L plus R, again, just to make sure that it is what we expect, and comment this out, this will now work. Because what we have said is modify the types of the procedure, right? Modify T to always be an S64. So what we've essentially done is just this. But we've done it specifically in modify. And if we uncomment this and run it again, we get number mismatch, type wanted int, type given float 32. Because we can modify T or whatever type parameters have been given to us, we can do some funky things. And I have an example of that right down here. So if I call weird, and I pass in, say 10, 20, like so, and I run that, we'll see that T, and actually I should probably print this out just to make sure it's doing what I expect, right? And so let me describe what's going on here. We have this special argument, and ignore for now the $sign at the start of the argument name. We have the special argument that says, hey, get the context of how this function was called. Everything I've highlighted is basically given to us as an AST node, which if you've ever looked into compilers is what the compiler uses to reason about your code. It's basically how the compiler sees your code, right? Jai gives us access to this very low level primitive so we can do greater introspection and weirder things if we want to. So we take this caller code, we get the nodes from it, which will actually return AST nodes, right? It returns code node, which is the base AST node. We make sure it's a procedure call, which it's always going to be, but it's just fun to do, a little check to make sure. We cast it to a code procedure call, which looks like this, right? It's a code node that has a bunch of different things in it, including the arguments or the nodes for the arguments. We grab the first argument and we assign T to be the type of that first argument, right? And all we do is make sure that type checking actually happened by making sure T is not void, right? If t was void, then that means type checking hadn't happened yet. And then we have another modify that just makes sure t is numeric, right? And so what we've essentially done is this, right? We have x of t, y of t, we return t, and we have a modify that is return type is numeric of t, right? This is essentially all we have done, right? The first example we had is the exact thing we have done here, except we've gotten the AST nodes, the type checked AST nodes, looked for the first arguments node, and then gotten the type that Jai inferred, right? So we've done this thing, right? So we've basically done this $t for Jai manually. If we change this to say the first argument, or sorry, the second argument, right? That would be the equivalent of us removing this t from x and putting it on y. So if I delete this, that should make a little more sense. But in this third example, right, in this weird example, we have defined the return type of t, right? Like we've said, hey, we're declaring t to be whatever we return, and we've set that to be the type of the first argument, right? And so in a weird roundabout way, we've type checked for Jai, or we've solved polymorphism for Jai in a very weird roundabout way. But that gives you power to do whatever you want, right? For instance, if we wanted to check, hey, is this used in an assignment somewhere? If I do x is 10, or sorry, x is weird, 10, 20, maybe I give that a type float 32, we could check if weird was called in a context where it was being assigned to a variable, and then we could check if that variable was a float 32, and then make sure the first arguments are float 32s, right? The first two arguments are float 32s, right? We could do all that through caller code. So I'll delete this because that's no longer needed. But there is one more thing I wanted to talk about with polymorphism in Jai that because of how it looks, it gets confused with another feature. So if we go back to our add example and do x $t, y, t, right? When the $sign is used in a type context, so in this case, after this colon, that means polymorphism, right? That means it is a polymorphic type parameter. It would be very similar to us doing this in a struct. If we use the $sign, though, in the actual argument context or in a value context, if I put it here, right, this will work, right? I can do x plus y, and that will work just fine. But now the meaning of x has changed slightly, where here it means, hey, t can be any type. $x means, hey, x has to be something we can bake in at compile time, or that is a compile time known value. So if I run my beautiful test with a print statement, and I do 10 and 20, this will work as expected. But if I now make x a variable, or the first argument a variable, and I try to compile this, I'll get an error, right? The declaration of argument 1 requires a value bake. It is declared with a $sign before the identifier, but this expression is not a bakeable literal. But that is the first difference. The $sign matters which context it's used in. We have said x needs to be a compile time bakeable thing, or a constant. Because what Jai will do is if it's a bakeable constant or a bakeable value, Jai will just do this, right? That's how you can think of it. It's saying, hey, x is some constant 10, and then, right, y is a runtime value, so add x to, the runtime value, right? In reality, it's actually replacing every instance of x with the literal value, but you can think of it as this. They're basically the equivalent. And now there is another case with the $sign. That is if I have two of them. And what this tells Jai is, hey, if we can bake at compile time the value of x, do it. Otherwise, we're expecting it to be the runtime value. And that has some, weird implications, but I can show you exactly what that means. So if I compile this, this will now work, right? We get 20 as we expect because, x is nothing, x is just 0, and we have our 20. Right, if I, set it to 10, we'll get 30, the same way as if I pass in 10. And let's actually introspect in these different code paths. So if I do a compile time if, and I say is constant, which is a built-in sort of function for Jai, for checking this specific thing, I can print, and I can say X was baked in, X was not baked in. And now if I run this, you'll see X was not baked in, but now if I add this 10 in, X was baked in. And so that is where what the $ means in the sort of argument context is, hey, if we can have it as a constant, give us it as a constant, right? And just as a quick little aside, you cannot do this in Jai, all right, the same way you cannot do this. These do not make sense. $, whether they're in the argument context or the type context, are only used in parameter lists. So I hope this is a video that was helpful for people, or I hope it just gave you more information about the polymorphism system in Jai, and I hope you enjoyed the video. So thanks for watching, everybody, and I'll see you in the next one.